What? I don't think you should be doing like this. You know, just to try to like change that.
Okay. All right. So now we're way behind. So today we're going to revisit a little bit of information theory that we talked about, things like that entropy that we looked at near the beginning of the course. And we'll dive into source coding, specifically look at prefix, media codes, and then we'll look at two different algorithms. As in everything, there's lots more to look at, but these are kind of your classic algorithms and get you off to a great start. All right, so why do we do source coding? First of all, I haven't even explained what source coding is, but it's a way of taking the information, right, that we're trying to communicate and putting it into its most efficient form possible to send it over the communication link, right? So now a few times in this course we've assumed that we've made assumptions where the bits or symbols are equal probable and found that that gives us a lot of simplifications. Well, not everything is equal probable though, right? So consider the letters of the English alphabet, right? They can be represented by the 8-bit ASCII code, even 7 bits if you ignore case and a lot of the special characters, but basically 8 bits, right? And that's going to give you all the US type characters. But I don't know how many Wheel of Fortune fans are here today, though. You don't make your big guesses on the letters X or Z, right? You choose E or T or S or some of the more very common letters. So there's probably some waste then in representing everything with these 8-bit codes if we know that a lot of times we're just sending an E. So if we go way back, Samuel Morse is generally credited with inventing the telegraph. And his Epiphanes Morse code is one of the earliest examples of source coding. And here we have, the Morse code printed out here. Of course, it's a series of dots and dashes, okay? And a dot is actually 1/3 of the length of a dash, right? So the dot, thing, right? So, and we notice here the E is represented by a single dot, right? And T, another common letter, is represented by a dash, right? So this was long before Shannon had published his results on entropy and that type of thing. But we see that there was already this intuition that common letters should be quicker to send. Because if you're going to send a big document or a big message, then you want to do that in as quick as way possible. Okay. And fun facts to know, it was a nice day Sunday, so me and my friend went to Greenwood Cemetery, and it turns out that Samuel Morse is buried there. So you can make your own pilgrimage there if you want. So by making the most common letter shortest in time, he minimized the overall time to send a message composed of a typical set of sequences of English language characters. Now, can we do the same? That's what we're talking about with source coding. By reducing the number of bits needed to send some information, we can get a head start on that capacity bound. Remember that? That says, Shannon says that at best, you can send this many bits per second, right? And you're constrained by the bandwidth, the signal power, and the noise power that you have to deal with. Well, that gives you the upper limit on the bits per second. If we can figure out how to reduce the number of bits to begin with in sending, then we're already ahead of the game, right? So that's really what we're about here. So now with the information theory, recall that the amount of information in a source is related to its probability, right? So if that event is certain to happen, has a probability of 1, well, there's no need to communicate it, right? We don't need to send that over the communication channel. We know it's going to exist, happen. Or, conversely, if there's no way that event is going to happen, again, we don't need to communicate any information about that. We know that. It's really when it happens in between, right? So we want to measure that somehow. Now, so let's talk about an alphabet, right? So I mentioned we have, the English alphabet, lots of other alphabets out there. That's really kind of a more generic term I would like to use. And it's going to be composed of different letters, right? Now, it doesn't have to be A, B, C, D, but it can be other kind of units of information that we want to send, okay? So take all you know about alphabets and letters and that type of thing, and then just try to make that a little bit more generic of an idea and not just your little ABC song you learned in kindergarten. So each letter in the alphabet has a given probability of occurrence. We're going to call that little piece of K, right? So that's the probability that the random variable X will take on a particular value X of K. And we've got this alphabet that's L long. So any of these letters, now it has to come from that letter. So if you sum up all of these individual probabilities, the probabilities, the sum of those probabilities have to equal 1, right? Because you're certain to be dealing with one of these out of that finite set in that alphabet, right? So it's just kind of defining some things here. So if a source is discrete and each output is statistically independent of each other, right? So in other words, at one instance, we might send X sub 2, and another instance, we might send X sub 8 or something like that, right? But there's no dependency or statistical dependence on one versus another, okay? So then we call that a discrete memoryless source, or a DMS, right? So and that's in contrast to a memory type of source, right? And I find it a little bit unfortunate that they use the M. Well, that could mean memory or memoryless, right? But that's kind of the convention, is to call it a DMS, or a discrete memoryless source. So now let's consider two discrete random variables, X and Y, with possible outcomes in the alphabets X and Y. So these would be the collection of everything possible, right? And these are random variables, so they can randomly take on particular values within that set or within that alphabet, right? So what is the amount of information that the outcome Y equals some instance Y provides about the event X equals little x, right? So we've got these two random variables. What is that conditional probability, right? What information are we gathering out of that? So this is kind of a longhand way of saying it. We're just gonna define a little shorthand there. And again, a long way of saying that the random variable takes on a particular value X, and we'll use a shorthand there also. Now we're going to define this information, okay? So this I and X semicolon Y is going to be the log of this conditional probability divided by the log of the marginal probability, right? So I know this is just a lot of math so far, right? But hang with me. So now, by convention, some people use log base E, or a natural logarithm. Others use log base 2, and so if it's 2, it's bits. If it's E, it's naps is a unit, but you won't run into that too often. And then you can always convert between the two, right? So, but that's kind of our fundamental equation there, defining I. So now if we look at that, that's the information for particular instances there, right? So what is the information gained there? And we can also now look at that for the random variable where these things can take on any value within that set, or every value within that set, actually, okay, with any alphabet. And we'll sum up those i's, those informations, but multiplying by that probability each time. So we can kind of step through this a little bit and simplify, substitute in, and we have this value there. Now, these are just some properties that it's commutative there, and that the information is going to be greater than or equal to 0. So the information that we learn about x given y, then it's going to equal 0 if and only if x and y are statistically independent, right? So if they're statistically independent and we know y, well, it still doesn't tell us anything about x, right? That's the nature of being statistically independent. And so also it's going to be less than or equal to the minimum of the size of these alphabets, right? So it's no, its max is not equal to 1 or anything like that. It's really the size of the minimum of those two different alphabets. Okay. I'm sorry?
What is the SI mean again?
Statistically independent,
Okay.
just an abbreviation. So,
Thank you.
yeah. When knowledge of y equals little y uniquely determines the occurrence of the event x, then that conditional probability up here is 1, right? So we're going to take this general equation over here, and you don't see that. So we're going to take this and we're going to make that equal to 1, that conditional probability up there, right? So then we can use a property of logarithms and take this quotient here and just replace it with the minus sign out there. And now we can do some simplifications. I'm just going to kind of rush through here because we've got a late start. But this is kind of the key idea here, that this information of the random variable x given y is equal to this negative summation here. We're going to call this the entropy, right? That's how we came up with that, or Shannon came up with that originally. So h of x is the entropy of capital X, and it's going to satisfy these constraints and properties also, that it's going to lie between 0 and the log of that size of the alphabet. And a few other things that I don't think actually we end up using a whole lot. So all right, so I'm going to give you a couple of theorems over the next few slides, and they're just going to be statements. We're not going to go back and try to prove them or anything like that. I think the proofs are in that textbook if you have access to the textbook. So Shannon's first theorem, the lossless source coding theorem, states that let X denote a discrete memoryless source with entropy X, okay, H of X, capital H of X. There exists a lossless source code for this source, and lossless is important here. We're not losing any information, right? At any rate R, if R is greater than the entropy of X, okay? There exists no lossless code for this source at rates less than the entropy of X, okay? So there are, lots of deep meaning in this, that type of thing, but here, what I think is important for you to know is that if we want to figure out how much we can compress this, it's going to be a strong function of the entropy, right? So that's really where we're getting at. So can we achieve or find a lossless source coding algorithm. We can do that for a rate greater than the entropy. So
Can you go back a little bit?
Yeah.
Okay.
yeah.
Thank you.
Okay, so then we have we want to look at a lossless coding algorithm with variable length source coding. Okay, so we're gonna this is just an example. We're gonna create a 4-letter alphabet, A1, A2, A3, A4, and they're not going to be equal probable. This one's going to be 1/2. And probability being sense, and 1/4, and then last two 1/8. Okay, so we could just do a 1, a 0, 0, a 0, 1, and a 1, 0. Okay, but well, have we really saved a lot in doing this? And what's going to happen here? We've got a 1, but we've got a 1 there, right? And so there's maybe some problems with this, right? Because we're going to want to take one sample over another, and we're going to, after another, we're going to send them, okay, across this channel. So we want to figure out when a symbol or a character starts and when it ends. Okay. Now, if we're at a very high level and we're sending big packets, well, maybe we put a header on the beginning of that packet that says how long it is, right? But that takes up space, right? So what we're trying to do here is figure out how to use variable length source coding so that we're going to send our most high probability symbols or letters out of our alphabet with the shortest coding, source coding, right? And our less common ones, A3 and A4, with longer ones, right? So this kind of makes that satisfies that. This one's just 1, but you know, we don't know whether if we see this symbol 1 and a 0, is that an A4 or is that an A1 followed by like an A2 there, right? So it begins hard to figure out. So we're going to introduce this idea of a prefix condition that requires for a given code word CK of length K having elements B sub 1 through B sub K, there is no other code word of length smaller than that. L is less than K with elements B1 through B sub L for all the way up to that. So what does that mean? Okay, well, you can figure it out, but the simple way of looking at it is that basically there's no other whole code word that appears as a prefix of another code word. Okay, so here we have a whole code word that appears as a prefix of the other one. Okay, another one. So this code 1 fails this prefix condition. Okay, let's look at this code 2. Right, so now let's assign the bit 0 to this letter. Okay, and now we're going to create a code word 10 for A2. Okay, and then 110 for A3 and 111 for A4. Okay, so A1's the most probable letter, and it's sent using the shortest symbol. So that's good, the shortest code word. And the lowest probability ones are sent with the longest code words. That's good, right? So we're being efficient at sending things. And there is no code word that appears as a prefix of another one, right? So this code word 0, there's no other code that starts with a 0. There is no other code word that starts with a 10. There's no other code word that starts with a 110. If you had a much bigger alphabet, that trend you would want that trend to continue if you wanted a prefix-free code. Okay, so here's another code this fails the that prefix criteria. Still might have some advantages, but you would have to kind of keep looking at it and make some sort of decision. Say, is this really A4, or is this A3? Is this one really A3, or is it A1 followed by something else? Well, as it turns out, these are all kind of unique, but you can't make that decision instantaneously, right? Over here, as soon as you see a letter, you know that as soon as you see a 1, you know it's not A3, right? But over here, you got to kind of keep looking to see. So there's some latency built up in that ability to make those conclusions on what code word is associated, with representing these letters, right? So at the receiver, we're getting these code words and they're all concatenated together, right? So we're trying to parse them out and get these. So this is prefix free, and we can also make that decision instantaneously. As soon as we see a 10, boom, we know it's an A2. As soon as we see a 0, we know it's an A1, right? We don't have to look and see what's following that. Okay, so now the question is, well, I toss up that code 2 and say that's prefix free and it's instantaneous, right? But how good is it, right? So that's really, as engineers, we want to measure things. We want to try to come up with the best solution within our constraints, budget, and schedule, and that type of thing, right? But we want to try to find that best solution. So we need to measure it and decide how good it is. So we're going to define this average rate, okay, of the code. And so this is going to be the average number of bits per source letter that we need to send that code. But it's weighted by the probabilities of each and the number of appearances there. So yeah, so let's now define or declare another algorithm, the source coding theorem for prefix codes. Let X be a discrete memoryless source with finite entropy H sub X and output letters A sub I up to N, with corresponding probabilities of occurrence P sub I, where I ranges from 1 to N. Okay, so for each letter, there's a corresponding probability of occurrence, right? It is possible to construct a code that satisfies the prefix condition and has an average length R that satisfies this. Okay, so this R is going to lie between H of X, or the entropy, and the entropy plus 1. Okay, so we don't know exactly how good it's going to be, but we know that we can get something in that range. Okay, so a lot of information there. Let's go through an example, and hopefully things will make sense here, right? So let's walk through a Huffman algorithm. This is a variable length code, and this is the alphabet that we're dealing with. And so this character is sent, or a letter that alphabet is sent 0.35 with a probability of 0.35, whereas these down here are sent with a probability of 0.005, right? So let's figure out, can we construct a code? So Huffman was a student and developed this as part of his project, and in lieu of having to take the final And his professor was this guy named Dr. Forney, who was almost as famous as Shannon. So he has lots of stuff associated with them. So, but Huffman, as his student, came up with an algorithm that was better than his professor. So that's your challenge. I don't have anything like Forney did, so it's not that high a bar to accomplish, right? So what we're going to do is we're going to start with our lowest probability characters. Let's see. Okay, gotta make sure I can restart this Zoom thing here. So and we're going to combine these, right? So we're going to have this little tree graph here, and we're going to build up this tree, and then we're going to read the code off of it, right? So it's kind of a step-by-step process. So we take this, we combine the two lowest probability events and or letters, and then we sum up their probability, right? So this is probability of either of those, one of those happen, right? And we're going to put a 1 down below and a 0 up above. And we're just going to kind of crunch this little algorithm out. Now we're going to do the same. Okay, so we look at 0.01. What's the next lowest probability? That's 0.04. So let's add those together, and we have a 0.05. Okay, and let's keep doing that. 0.05 and 0.1 gives us 0.15. 0.15 and 0.2 gives us 0.35. 0.35. Well, it's actually bigger than 0.30. So let's take this 0.30. It's the lowest probability, then the next lowest probability at this point, right? So this probability is higher than this one. So we're going to take this and we'll combine it with that. Okay, yeah, so it's happen to be the same, but we just pick one and we combine those. And now that's 0.65. And then we combine those, and of course that's 1, right? It should be 1, right? Because we've got to send one of those symbols, right? So, all right, so now we read off of this graph and fill out our code here. Okay, so we've got 7 of these, I think, if I copied all this over right, and our probabilities are right there. And let's read off our code. So let's start at the bottom here. We have we'll start over here, and we have 1, 1, 1, 1, 1. Okay, 1, 1, 1, 1, 1. Okay, let's follow a different branch. 1, 1, 1, 1, 0. Okay, associate that one with 6. Okay, 1, 1, 1, 1, 0. And then 1, 1, where are we at? 1, 0. Okay, so 1, 1, 0. Did I count right?
Yeah, the next one.
Yeah, okay. And then we have here a 1 and a 0. And here we have a 0 and a 1 and a 0 and a 0. Okay, so and then this is the self-information. We'll skip that right now, but if we go back to that formula, we can have an average, I should have a bar over that, but a rate of 2.21. What does that mean? That's an average number of code word length that it takes to encode this overall, right? Weighted by the probability. Okay, if they're not weighted, then we're not doing source coding, right? If everything's equal probable, then we don't have to really do this. Okay, so here's another example, right? So here we're going to traverse this. It's basically the same problem, right? But when we get up here, we will combine this 0.35 with 0.3. Okay, so remember when we got to this point in the previous one, I said, well, that's no longer the lowest probability, that one is. But I noted that these two were the same, and in the previous one, we just did 0.3 with the 0.35. But there's nothing wrong with taking this 0.3 and combining it with that 0.35, right? It's kind of the same, so we had to make a choice. Who can simply make this choice now? And we'll see that things still work out, but it's going to be a slightly different code, right? So if we look at this, it's starting at 0, 0, 0, 1, 1, 0, and this other one, it's basically taking the same thing, but it results in a slightly different code. It turns out that the rate's still the same, so it doesn't really matter there. So all right, and then there's the another example here. So here we have a different set of probabilities, and so this one's going to be just a little bit more complex, but it's the same algorithm, right? So here we start with 0.02 and 0.04. We combine those. These are our lowest two probabilities, right? So we're combining those to be 0.06. We'll write a 1 there and a 0 up there. And then we look at this 0.06 and we find the next lowest one, that's 0.09. So that gives us 0.15. Now here, we look for the lowest probabilities, and oh, well, it's not even that one at all anymore. It's this 0.1 and 0.12. So let's combine those to a 0.22. We're still assigning these numbers in a consistent fashion, right? So, but we're just still building up this tree. So that's 0.22. Now let's look, what's our lowest probability? Okay, well, we got that 0.15 there, 0.22 there, but we've got a 0.13 and a 0.14. So let's go ahead and combine those two as the lowest probabilities, right? And so now that is 0.27. And now let's look through. All right, so now the lowest probabilities are 0.15 and 0.22. Combine those at 0.37. 0.27 and 3.6 is minus 6.3. We double check that these sum to 1. Okay, so now we built our tree. The tree is complete, and now we can just read it off again. You have a question?
Yeah. What did you start from 0.15 and not 0.06? Because 0.06 is the lowest probability.
Yeah, right here.
Yeah.
Okay, so yeah, we start with these two lowest ones and we combine them, right? And that produces this probability. Then we look around and say, okay, well, that's still the lowest, and the next lowest is this one. So let's combine those, and that gives us 0.15. Now let's look for the next two lowest probabilities. There's 0.15. But both 0.10 and 0.12 are lower probability than this one. Okay, so we hold off on here. The next step, at each step, we're looking for the two lowest probability events to occur. Okay, so then we do that, and then now we kind of evaluate again. We look around. That's 0.15, 0.22, but these are still lower, right? So these are still the two lowest probabilities. So let's combine those. 0.27. Again, keep looking through. And now our lowest probabilities are 0.15 and 0.22. Do that one, and then 0.27 and 0.26, and do that. Now we built our graph. We double checked that those probabilities sum to 1. They should, unless we made a mathematical mistake. And we write out our code. So we can start anywhere, but let's start at the bottom. We've got a 1, 1, 1, 1 brings us to this letter here. That's x of 8. So we have 4 ones, right? So we can just follow this graph, this tree graph, right? So 1, 1, 0. Well, I'm sorry, 1, 1, 1, 0 brings us to x of 7, 1, 1, 1, 0, and 1, 1, 0, 1, 0, 1 brings us to this one, right? So 1, 0, 1, 1, 0, 0, and then that's that's all of this branch, right? So when we go up here, we have 0, 1, 1, 0, 1, 0, 1, 0, and then 0, 0. Okay, so now we can, now calculate our rate, and we've got a 2.7 rate for this particular alphabet, right? So what creates a unique code is going to be the size of the alphabet and the probability of each letter in that alphabet. You change the size, or you change the probabilities of any of those letters, right? Then you're going to end up with a different code, right? So, but the algorithm is the same. You just crunch that out. Okay. So, I'm actually, in spite of getting a late start, we're actually moving through this pretty quick. So maybe it'll be an early day. Because it's hot in here. It's not as hot in my living room when I'm giving these. All right, so can we get even closer to the limit? Yes, we can, by encoding blocks of J symbols at a time, and then letting J be large. It's kind of gonna just kind of skim over that one because just feeling like we weren't going to have time, but basically you can encode these things in blocks, and then the larger blocks you have, then the more efficient you're going to be. But if you're creating these long blocks, then you're going to have some latency in decoding these things, because you've got to now look at that whole block before you can make a decision. Do you have a question?
So you always assign one to the lower branch?
Yeah, by a convention. So just be consistent. So everything I look at does these ones at the bottom, right? So there's not really a choice you're making there. You're but the idea is you're building up this graph. Okay, and so you build up this graph using that algorithm, this tree graph, and then you're reading off those bits. Okay,
Thank you.
so the Huffman coding algorithm is actually optimal. Right? It's not just a good one, but it's an optimal one, right? So our job's done, right? We don't need to look at it anymore. Well, it's only optimum in certain conditions and in certain contexts, right? So it is optimal in that it produces code words that satisfy the prefix condition, right? So as we're decoding it, we see this big long stream of bits coming at us. We can unambiguously extract out what those letters were that were sent, right? And so that's good. And that the average block length is minimized, right? So we're looking at that R value, that capital R. So we're trying to encode that overall thing, that overall alphabet, with as few bits total, right? When we weight that with the probability of each letter in that alphabet. Okay. So now the challenge is that we need to know the occurrence probabilities of the letters in that alphabet. Okay, and that's not trivial. Okay, so for those watching online, I'm going to stop this Zoom session and start the next one. So